Let's begin our first objective, shall we? Where we are being able to use this sigma notation to write and evaluate a sum. And the things that we are usually summing are a sequence of numbers. And that sequence of numbers, generally in mathematics, is denoted with an a sub 1, an a sub 2, an a sub 3 for the first, the second, and third, all the way up to a sub n, where we have n terms in our sequence. Okay, so if I wanted to, for whatever reason, add up all n of those terms, a compact way of writing that is with a sigma notation. It's this capital Greek letter sigma, which looks like a fancy E. All right, so there are essentially three parts to the sigma notation. You've got the bottom part here where it says I is equal to 1. You have this top part n, and then inside here, the sigma notation, this is the generic term of the sequence. Okay, so this I that's down in the bottom is called the index of the summation, and it's essentially the variable for the summation. It's the thing that changes. And now it doesn't change by real numbers, it changes only by counting numbers. And the one that is right here beside the I equals 1, that's the lower bound of the summation. It is telling you where to start counting. I'm going to start counting at 1, and then I'm going to increase by integers 1, 2, 3, until I get up to n right up here, which is the upper bound of that summation. Now, sometimes this is an n and it looks like a variable, as in I'm going to keep it generic, or sometimes it is a number. I'm going to start from 1 and I'm going to count up to 10, or I'm going to count up to 100. Okay, inside the sigma notation is the generic term for the sequence, the a sub ith term. Now, usually when we're talking about a sequence of numbers, we call the generic term the nth term. But in this particular notation, the nth term refers to the very last one in the sequence. So if I want a generic one, we're just going to use the ith term. Now, speaking of I, as an index for a summation, the most common ones are I think our book uses K, and possibly J. Those are the most common ones. And then the most common lower bounds, the places to start counting. Well, it makes sense to start counting at 1, but sometimes we start counting at 0 instead. All right, so let's, now that we have kind of the notation down and the parts of the sigma notation, let's try this on a couple of sums here. We want to expand each one of these sums. We've got about 4 of them. I know it looks like 2, but there's really 2 more after this. All right, so I have the summation from I equals 1 to 6 of I. I is like our little function here, and this counter I equals 1 tells us where to start. I'm going to start with I equals 1, and notice that when I just plug 1 into this, I just get 1 as my function, plus, and now I'm supposed to increase this counter by 1 more, and then stick that into the function here, which is just going to be a 2. Plus, and then I increase it by 1 again, 3, plus 4, plus, where do I stop? Stop right here at 6. 5 plus 6, and then I total those things up. All right, so let's just total these things up. I like to do this by grouping by tens. Let's say you got a 10 there with a 4 and the 10. 2 and 3 is 5, and the other 5, there's another 10, and then you have the 1 left over, so you got 21. Now, since this is essentially the same thing as that Gauss formula that we came up with, it was n times n plus 1 divided by 2, we could do n, which is, let's see, our n is 6 times n plus 1 is 7, and then divided by 2. 2 goes into 6 3 times, which gives us the 21. Wow, fantastic. We got the same number. All right, let's look at number 2. So here in this example, instead of counting starting at 1, we're going to count starting at 0, and we're going to go up to 5. And this time our ith term is defined by I plus 1. So we'll start by taking this I here as the variable for the summation and plugging it into this little formula. And the first term of our sequence is 0 plus 1. plus, and now I'll increase that counter by 1. I'm going to go up to 1, plug it in for I here, and the next term is going to be 1 plus 1. Plus, again, increase the counter here by 1 more, so I'm going to go up to 2, plug it in for I here, 2 plus 1, and so on, and I'm going to continue until I get up to 5. So I'll have 3 plus 1, 4 plus 1, and then finally 5 plus 1. All right, let's say that I total up each of these sets of parentheses. I get 1 plus 2 plus 3, 4, 5, and 6. Well, that looks totally familiar. Isn't that essentially the same thing that we just did right over here? That should total up to 21. And notice that this is essentially the exact same sum. It's just that we've basically translated where the index here, we translated it to the left 1. So we're going to start at 0 and count up to 5 instead, but I still end up at the exact same sum. All right. And sometimes that might be something that you have to do because a summation only, the little formulas that we're going to have, they start at 1, but maybe the sum that you have starts at 0. So you can take your sum and then just kind of translate it to the left or the right if you need to. All right, let's look at the second set. All right, slightly more complicated here. Now, this time the index is k. So remember, k is the variable for the summation. It's the only thing that changes, and we're going to go up to n. Now, n I don't have a specific number for. We're just going to keep it generic. So the first term in our sequence, I'm going to take this k equals 1. I'm going to plug it into the set of parentheses here, and I'll have 1 over n times, plug the 1 in here, 1 squared plus 1 plus, okay, now I'm going to increase this counter by 1. It's going to go to 2, and that's going to go in here for our k. 1 over n still stays. It doesn't change. It's not a variable. I've got 2 squared plus 1 plus, and I'm going to continue doing this until I get up to n. So the next one is going to be 1 over n times 3 squared plus 1 plus dot, 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 and I keep going. So the dot, dot, dot is the whole skip a few thing. So it just follows the same exact pattern. Plus, and then the nth one would be 1 over n times n squared plus 1, because that's where we're supposed to stop, right? We're stopping here at n. Now, notice that every single one of these terms has a 1 over n in common. So one of the things that you could do, this is going to be important later, is that you could pull that thing out, 1 over n times, and then you would have the summation from all of these little parentheses, 1 squared plus 1 plus 1 squared, no, not 1 squared, we already did that one, it'd be 2 squared, plus 1 plus 3 squared plus 1 plus skip a few plus n squared plus 1. Okay, not only that, all of this can be rewritten in sigma notation because it's a sum, and then this part right here is just kind of like a coefficient that gets multiplied by all of them. So one of the things that I could do for this particular sum, and again, this is going to be something that will come up shortly here. I'm going to get rid of this and then just change that to the summation from k equals 1 to n of k squared plus 1, right? So essentially this is a constant. It's the same number every single time, and it will be common to every number in the product. And then just using the distributive property, basically, we would pull it out. And when we do, we can see that if I have a constant, I can pull it out of the summation, right? That's exactly what happened. All right. Whoa, take a look at number 4. Maybe I need an extra piece of paper for this. This looks totally strange. This looks intimidating, but don't let it intimidate you. It's the same kind of thing, right? So we're just trying to establish like a familiarity and some experience with what we're supposed to do with this little sigma notation. So our variable is back to I, starting with I equals 1, and we're going to count up to n. And the only thing that's changing here is the little subscript. So notice that this x here, sure, it's a variable as we usually think about it, but for this, the summation is not a variable. We would have some sort of function that we would be plugging x sub 1, x sub 2, and so on inside of, but for the summation, the only thing that's changing is the subscript on this. So look, the first term of our sequence, starting with 1, is going to be f of x sub 1 times delta x. It doesn't change. Plus, the next term is going to be f of x sub 2 times also delta x. Plus, maybe I do another one, f of x sub 3 times delta x. Plus, and then let's skip a few and go up to the nth one, which is where we're supposed to stop. Whoops, no, not that. That is not how you read this. Okay, fix it. X sub n times delta x. All right, this looks strange. Like, why the heck would we want to sum? Hey, what are the things in this sum anyway? Here, let's just see. This right here, isn't that a function? Yeah, that's a function value. And then what's the other part of this thing? Well, let's see, we got a delta x. This is a change in x. So if you think about it in terms of slope, here, let me maybe sketch out something real quick here. If I have myself maybe a line, and on this line, I draw in like a little slope calculation. This little width right here, that's delta x. That's the change in x, right? So this delta x represents a width. And this function value, that function value, wouldn't that be a height, right? It's a height off of the y-axis. So what you got here is a function value that's multiplied times a width. I wonder how that could be used. I wonder, is there a connection between that and our second objective about finding an area? All right, well, I don't know. Maybe eventually we'll make some sort of connection. In the next video, what we're going to do is we're going to look at some formulae for all of the different kinds of sums that we'll use for the rest of the lesson.